So let's officially start. Hello, everyone. Welcome to episode 29 of Warsaw.AI Meetup. My name is Pavel. I will be the moderator today. Before we start, I would like to thank our partner sponsors, Allegro Tech, for hosting us again. Nomagic and DataArt will have speakers from both partners from both Nomagic and DataArt today. So we have opportunity to listen to their interesting talks about the projects. And I would like to announce a few initiatives that we have in plans for 2026 beside the next Warsaw.AI meetups, of course. There will be the third edition of the contest for the best AI thesis in AI in Poland. So actually currently we have the second edition. It's ongoing, and there will be the announcement of the results around April. But for October this year, we are already planning the third edition. There will be the second edition of the AI intern program, which is a matchmaking program for online AI internships. Hopefully, we'll organize the second edition of the Warsaw AI Hackathon. So we had a successful first edition at the end of November. Who of you attended the Warsaw AI Hackathon? Okay, we have a few people with us, great. We invite you to subscribe to our weekly Warsaw AI newsletter. And in April, there will be the third edition of our quantum machine learning workshop. So if you are interested in quantum computing beside AI, then we invite you to attend. It will be online. And this is the plan for today. So first, Łukasz Staniszewski from Ideas Research Institute and Warsaw University of Technology will give a talk about controlling generative models through mechanistic localization. Then Andrii Bilous from DataArt will tell about reliable LLM systems for real-world data extraction. And then Michał Grzejdziak-Zdziarski from Nomagic will tell about scaling physical AI for 99.9% reliable warehouse automation. And later will be the after party, so I hope you will stay with us. And today there is a strict deadline for the after party until 9:30 p.m. After every talk, there will be time for Q&A, about 5 minutes, so we'll have opportunity to ask questions. And we can start. So let me invite our first speaker, Łukasz Staniszewski.
Okay. Hello, everyone. Thank you for coming. My name is Łukasz. I'm currently doing my PhD studies, and daily I work at Ideas Research Institute in Warsaw here. During my PhD, I'm mostly working on generative models, and as there are many fields next to generative models, what I'm really curious about is how to understand what actually happens inside those models and how can transfer the insights that we collect from these understandings to some methods for controlling models and aligning them with human intent. So to start with some motivation, you are probably aware even better than me how great current AI is, what quality of content can we get from those closed source models, for example, Sora 2. But open source models are also really great. You can already adapt them, even some open source models on your own computer and make them, for example, generate your own images. But those amazing technologies, I think, have also the other side, which is that when inappropriately used or used against our intent, they can be used to cause harm. For example, by generating toxic content on the images, or for example, sharing some fine-tuned version of our models or models that were generated that were trained to generate nude versions of some celebrities, as you probably seen on X platform recently. So I think that we as humans, as researchers, have a new fundamental challenge to face, which is to try to understand how to control technologies that are actually designed to surpass our boundaries of understanding and intelligence. And I really like this quote from David Bow, who is, by the way, a great researcher. And he often highlights this fancy word resilience. And in his words, resilience is about how the system responds when something completely unexpected, something that we couldn't anticipate before happens. because if we would made our all S systems or ecosystems around AI resilient, we would be able to continuously adapt to those unexpected challenges that will happen in the future. And David suggests 3 directions that we could pursue to make our ecosystems resilient, which is fully understanding what AI is already doing, even though it's some black box after fine-tuning. We would like to have, and we would do it because if something goes wrong in our system, we would know exactly what is the part that needs to be fixed. The practical control over the AI, so that whenever something goes wrong, we know how to fix it. And the power over AI, which is some kind of skill set, tools, and people who can actually make this change and fix everything for us. And my argument during this talk is that one approach that we can take to pursue all those 3 directions simultaneously is by doing localization, or especially mechanistic localization. Maybe we can start with what is localization even about. So our neural networks that we work with are some huge mathematical functions that have some input, for example, prompts in case of text generation models, and they generate some output. And we know that if we slightly manipulate our input, the output will also change. But it's high level, and actually we can understand also them as some computational graphs that have some intermediate mediators, such as neurons or layers, through which the signal propagates, and that's how the generated signal happens. Causal mediation analysis is actually the root for the localization, and it's about how we can slightly modify those mediators, single neurons or single layers, and study how our response variable, so the output changes. And why would we even want to do that? So yesterday I asked GPT-5.2, to tell me where Norbin factory is, and apparently it knows exactly where it is, where we are now. So maybe it would be pretty cool to understand how exactly this model, maybe not this model because it's a closed one, but GPT model knows this stuff. And something that can help us is the paper from 2022 from NeurIPS by Kevin Mock and his colleagues, who simply tried to do that. And we can do it by analyzing the computational graph, or LLM. Our LLM is usually some autoregressive transformer. So it inputs some tokens, propagates these tokens one after another, and finally, as the last token, it will output probably the most probable continuation of our prompt, right? So our transformer is consisting of attention layers and MLP layers. Through them, the signal is propagated, and some hidden states between those layers are actually what interests us. And that's how this model works. And we can call it clean run because it's how we expect the model to work. So now imagine a bit different experiment where we will, for example, noise or cover the tokens that are regarding the subject that we are actually studying. So in this case, Norbin factory. What happens with the model? The model will probably output gibberish because it doesn't know what actually is it asked about. So we will call it corrupted run. And these guys, in their paper, they decided that they will simply try to see which parts of this computational graph are important to recall this Warsaw, even though the question is actually corrupted. And they can do it by simply transplanting those hidden states in the middle of computational graph to the specific point and observing the probability of token Warsaw at the output, right? After doing so, we can actually see that there are 2 points in our computational graph where this association between Norbin factory and its location Warsaw happens. It's at the beginning layers when we finish talking about our subject, which is Norbin factory, and at the exact end of the computational graph. After that, we can disentangle rows of attention and MLP layers in those signals, and we can see actually what happens is that MLP layers are important in this early side of our trace when we finish talking about the subject, while attention layer is at the end of this process. Why do we do that? Because after that, we can actually better understand what is happening inside of those models. And for example, MLPs are the one which are some kind of key to value mappers that recall some memorized properties of the subjects that we study, like the Norblin factory. And this property may be, for example, localization, which is Warsaw. So thanks to this experiment, we could say that they could say that knowing is what actually mid-layer MLP do, while attention layers are the one that copy this information that MLP accumulated to the last token, which is actually the output. So their role is saying. And thanks to this fact, we can, for example, use this information and propose how to change the model knowledge without even fine-tuning it from the scratch, by simply taking this layer that was important for this factual association and inserting new association. For example, in a case when Norblin factory is moved to Krakow. How we can do it? Because we have access to only one layer that stores this knowledge. We can simply unroll this MLP layer, take this output linear weight matrix that is actually doing this association, and slightly change it in a way that now for the Norblin factory, the output will be Krakow, but not everything that is in Warsaw will be now in Krakow, right? Because we don't want to do that. So I think this really easy experiment which they conducted show you that two things. That first, we can understand what model does by doing some localization, but also thanks to that, we can derive some really simple method how we can completely update the model without doing such a huge fine-tuning. So for us, probably autoregressive models are solved. We know how to update their knowledge really easily. And maybe how about the image generation models? Can we do the same? So image generation models are maybe a bit more different because, well, I will be focusing on diffusion models. So they work in a way that we sample some noise, and after some steps, we will end up with some image. And they consist not only of those attention and MLP or ResNet layers, but also with cross-attention layers. And these cross-attention layers are actually the layers that are important in this case, because they are the only one connection between the prompt, so what we ask the model to generate, and the image that is generated. And Basu and the colleagues in their work from ICML showed that we can actually use those cross-attention layers to see which one of them are really important for specific concepts or styles encoded in model knowledge. How we can do it? We can expect that if we pass the same exact prompt to all the layers, probability that the image that we generate is similar to Van Gogh, if the prompt is Van Gogh, is really high. But what if we find one layer that will be inputted with a bit different prompt, which is the same exact prompt, but omitting this Van Gogh style, and how will the image change? And by doing that, they found out that there are some specific layers in those big architectures that generate images that are really responsive to specific styles or objects, so that we can only touch those layers, modify only those layers, and change completely the model as we want it to do. So you may ask, why do we even want to do that in text-to-image models? So you can see, for example, that's probably the Stable Diffusion 2 model. So if you ask it to generate Snoopy Dog or Van Gogh style, it is capable of doing that. But what if it's our model and we don't have license or license for such trademark concepts? We would like our model to remove it from them. So knowledge editing can be understood as unlearning model from some stuff that it learned during fine-tuning, but we couldn't share it with the people, or by updating model knowledge when asked about British monarch or USA president after the elections. So it is pretty powerful, and in the same way as in text generation models, it is really cool because you only modify one or two linear layers. You don't have to have a really long optimization, multi-step optimization process to do that. You can only derive one form, the closed solution for that, and have one math equation that does that for you. So it's pretty fast. And in June 2024, as far as I remember, there were a really big model that was released by Stability.AI, which was Stable Diffusion free. And it was the first open source model that was actually really good in generating text, as you can see on the images. And I already spoiled it to you at the beginning, but when we took this model and in our paper and we checked it, we found out that it's such a great model that it can generate actually everything. I especially covered those all images to not get banned on YouTube. But honestly, the images, this model generate what you ask them to do. So it can be really used with a really bad cause. And that's why we decided that we will probably try to see if we can do something about that. And in our paper from 2025, we decided that what we first will do is we will check if those methods from the past can be used to simply detect those layers that are important for text generation. So imagine that you have some prompt that says one word and you apply it to all the layers of the model. You can see that it generates the text that you want it to do. And we repeated this experiment, applied it to one specific layer, a different text, and we found out to the one layer, and we found out that that actually the only thing that changes in the images when you do that is you change the text that is on the image. We applied it to two different architectures that are based on units, and it worked every time. That was something really weird about those models, that like using one or two layers among like 70 of them was enough to simply modify this content of the text that is generated. Later on, as I mentioned before, there were different architectures such as Stable Diffusion free, and they are based on a bit different architectures than units. And the biggest problem with them is that we couldn't have this direct connection in each cross-attention layer to the target prompt, to the prompt. So because they only input the prompt at the beginning and they process them by themselves. So we had to find a new way how we can control the text on the images with such architectures, which were actually the best on text generation. So we proposed a two-stage process that was highly inspired by this first work that I introduced, which is first we created one run, which was with the text that we would like on the image to happen, such as word Krakow. And we simply cache the activations, intermediate activations of the run. And then when generating second image, we simply choose one layer to which we decided to patch the activations from the first run to the second one. And again, it worked out really good. And as you can see, even those models that generate a really long text, maybe not really long, but long text, they are still, you can still change them and only them by using this activation patching. To sum up it a bit, those localization results, we went through different architectures and we found out that what is really common to all diffusion architectures when it comes to text generation on the images is that actually you can find a really small percentage of the layers that are really important to this text generation. And especially if you sum up the parameters, it's like less than 1% of parameters that are actually used to manipulate this content, which was pretty weird, but cool. As I promised, the goal was to how to fix actually the problem of generating this toxic text on the images. So first, what we did is we took some approaches that were, for example, created to, let's say, remove nudity or murder or blood scenes from the models. And we found out by applying such methods as negative prompting or safe diffusion isn't enough for such architectures to remove toxicity score. And that's why we proposed our approach, where we simply filter out the text with our method and only change it to some, let's say, more safe word on the image. And what happens is that we kept the generated image the same, but the toxicity of the words generated wasn't repeating on the images, which partially solved the problem. As I tried to mention it all the time, this approach is really good. This activation patching based approach is really good when it comes to controlling textual content, but it's not the same as controlling text. For example, by doing activation patching, you can't add text to the image, change position of the text, or change the style of the of the text, which is pretty bad. And additionally, this localization process isn't maybe as long as fine-tuning, but still it takes some time. For example, to find important layers among 50 layers, you have to perform 51 inferences steps. So it scales linearly with number of layers that we look through to find those important layers. But really interesting thing is the fact that actually many concepts and many skills that the model do are actually localized and specialized in singular layers, which is maybe a bit non-obvious. And can we make this entire process faster? What we found out also is that it's true that we can, because if you think about cross-attention layer, especially in vision transformers or the models that somehow connect text and images, you can use them, for example, to find segmentation, to do segmentation, and to find which pixels of the image corresponds to which tokens in the prompt. And we, for example, found out that when using those layers that are important for text manipulation, they were really good at segmenting the pixels that are responsible for text from other sides of the image, while other layers couldn't do that. So that's why we expect that like in the future, the methods that will be done for localization can only like look at the attention outputs and see how well those attention maps actually segment stuff. And based on that, we can probably find the layers that are important. And maybe you may ask, how about models that generate audio? Is it also the same? And we did same experiment, but for two models that are generating audio or music. And we used a bit different method than before because we had to use clap similarity, which is clip, but for audio. And we found out a really weird thing, which is that every concept that you ask the model to generate, it tends to specialize in the same layers when it comes to control over this concept, which probably suggests that those architectures are largely over-parameterized, and probably we could get rid of 90% of cross-attention layers to have the same, actually, to the exact same prompt adherence in our generations. So to sum up what I tried to say during this presentation is that, we should make our AI ecosystems resilient, because that's the only way probably how we can adapt to the unexpected challenges in AI. And this can be achieved by localizing these key components that are responsible for specific tasks or specific concepts. This localization is possible across many modalities. We checked text, image, or audio. I expect that video and other even different modalities are also possible to do that. And those localized layers can be effectively used for many downstream tasks. We used it for image editing, robust fine-tuning, removing toxic content. Some prior works used it for editing and learning or personalization. So it works. Thank you for listening to this talk. I leave for you the QR code for the paper, or to contact me if you have any questions. If you would like to know how you can easily do it, such tracing, I highly recommend using NNSide library. You simply, which is the library designed for LLMs, you can simply import diffusion model, load the model, choose which exact layer of this model you want to intervene upon, and instead of generating one image, you can, in the middle of this process, for example, zero out outputs of the one specific layer that you want and see how the generation changes. Oh yeah. Okay, so that's all I wanted to say, and thank you once again.
Great, thank you, Łukasz. All right, it's time for questions. Do we have questions? Okay.
So thank you. It was a very interesting talk. I have one specific question. You showed us that a specific layer is important for a specific word, like Warsaw or Fabryka Norblina, right? Now, is it in the context of this specific prompt, or is it for this specific word? Is it consistently the same layer?
Okay. Maybe I a bit. There was a bit misunderstanding, but What I'm trying to say that is any words are actually, when it comes to generating textual content on the images, any words are actually encoded in those layers. So whatever you prompt use, you can use those layers. Whatever change in the image you want to do, you use those layers and it works. So they are common for any prompts for any text.
For any word, you have a single layer that
Yes.
that drives
Yes.
it. Oh,
They are common for every text edition that you want to do.
oh, that's super interesting.
Yeah.
Okay, one more question.
I have one question about is one specific fact localized always in one place in the net, or does it happen that it's in multiple places? So if you change like one layer, it's still like this connection between Norblin and Warsaw is in other place.
Yeah. So what they did in their work is that they usually find out it's better to modify, for example, 3 consecutive linear layers to do that, but it's really one next to each other. So yeah, it's enough to edit this one specific layer, and then your fact is changed completely. So it doesn't arise in different parts of the graph.
Hey, I have a question because I run quite similar in the nature experiments connected with the, for example, truncation and ablation studies only on the text-based models. So multimodal was included in terms of the models. However, the test was run only on the text. What I noticed is that it is what you discovered. It's very dependent on the specific model family. For example, I'm not sure if you check with Gemma from Google. It has residual connections from the initial layers to the very last layers. It means that the gradient and the attention is being accumulated in this layer, which destroys completely the reasoning and any type of the prediction of, for example, I worked on that how truncation is impacting, or how truncation is impacting accumulation of the information. And if you have such unusual, unstandard approach in terms of the residual connections, because residual connection is something what is breaking the whole logic behind, it might be, I'm not saying useless, but it has to be per model family. It might be per model family, and it's very difficult to say, for example, I have model A, model B, how it will behave, in which layer will be accumulated the information, or which layer you need to touch to make specific change. This is something what you also discovered, like it's per model family, per model?
Yes, so it's probably hard for me to compare how one architecture is different from the other, because I fully understand, I fully agree. Yeah, actually, I think this paper that I'm describing here, it later on got a lot of criticism because some things weren't generalizing well for other architectures or further GPT versions. But for example, in case of those diffusion models, I think there is some connection that, for example, sorry, I need to move to the specific. So, for example, these two architectures are units, and you can see, for example, by looking at the index of the layer or percent of the layer, those are actually upsampling blocks that are important for that, right? So I think there are some connection between those models, and the biggest connection is that it's always brittle no matter what architecture you use. But yeah, maybe in text generative models the things are a bit different, right?
Let's connect later on. I can show you the results so we can exchange experience. Thank you.
Okay, thanks. All right, our second speaker, Andrii, is ready. So let's thank once again Łukasz. Thank you.
Hello, guys. Nice to meet you. Nice to be here. So my topic is like reliable systems, LLM system for real world data extraction. It's really sounds really strange. Well, it's difficult to understand, but this is like data parsing. So this is the most common, one of the most common tasks that enterprises use now use now with LLM. So instead of they could use parsing for LLMs for parsing. They could use RAG chatbots and this systems could solve a lot of pains. For example, well, this about me. I'm more than 6 years in software development, 3 years in AI/ML engineering. So I'm working as a senior AI/ML engineer at DataArt. And now we do actually this project. So we parse data from the large enterprises. So the question for you, what is the main problem with large language models from your experience? What's like the pain that you like experience? Maybe. Sorry? Sure. Yeah, exactly. And we could like paraphrase it as it's unreliable. So you don't expect the same result each time when you run it. And for data parsing, data extractions, that's really crucial, because sometimes this is the case. So we have invoice, date, corporation, some license, total. So we just want this document to transfer to JSON, not something like not fine tuning, no teaching your model or something like that. And it's really the pain. A lot of documents enterprises have. That's healthcare, in finance, invoices. Some I'm working with like in tourist industry. A lot of documents, they don't want the employee to parse this, because it's really the most boring task you could have. So we do this. We create the golden set documents. I'll tell you later. And a lot of mistakes that people do in this task, because it's so boring. So what is well, this is consequences that you don't have appropriate results, bad data, bad decisions. Okay, so one number is incorrect, it's harmful. Users lost trust fast. Okay, it's an enterprise, and you don't want to make it happen. And manual fixes are expensive, and they don't guarantee anything. So it's okay. I fix this. I fix this document. I trust me. I fix it. Okay, we found another bug in this document, because that's the people. Okay, so. When you want to use this, there are two types of parsing: rule-based parsing. There are services that make rule-based parsing. They don't use LLM, and when you could classify your documents. For example, you have pretty standard documents, like some tables or some text. They're standardized, and use rule-based parsing because it's deterministic. So you write your Python or JavaScript or whatever you want, and you expect by executing this code, you could have some test cases, a lot of things, and you don't spend money for tokens. Well, this is really important topic, because LLMs cost it's expensive. And what the problem that corporates, they don't have these types of documents. They have unstructured documents, legacy code. You work with legacy code. I'm sure that everyone had this experience, and we need LLMs for that, for unstructured data. So, okay, 2-3 types of documents is okay, but when you have unstructured, when you have some type and subtype and subtype of subtype the document, and you don't want to classify it, it's better to use LLM. So, okay, different outputs every each. Okay, run 1, run 2, run 3, and you have different types, different data and numeric data. This is because it could be, for medical reasons, it could be really harmful. 4 pillars, okay? how we do this, how we show that client have this like benefit from that. Golden set. Okay, the first pillar, golden set. Then we do pre-processing, multi-prompting, and post-processing. So each stage is really important. Golden set. Well, also very hard to create them because it's so boring that someone you like, okay, please create golden set, and often customer, it doesn't know what the expected result is for that documents because, well, there are like bugs in documents, and so creating golden set is really crucial because we will measure our framework based on that golden set. So and you should start, when you start parsing as LLM, you should start with golden set, and that will be not easy because we acquire in this job the business analyst, QA engineer, someone who will part this, a lot of discussions, and mostly, but without that, that could be the blocker for your project. And we have this blocker currently, well, and we experience that. So 100 verified examples. Okay, not 100, maybe 50, but you know, well, this is okay. About golden set. It's okay when you have 20. Okay, so not 100. Well, it's two big numbers, but it's an ideal case. Golden set. You have this ideal data, and then you could start creating your framework actually. So pre-processing. Okay, you could like run your LLM without pre-processing. So you generate simple prompt, paste your PDF, you like parse your PDF with some library like PyMyPDF, and okay, the prompt like read this is basic structure, and you'll have the accuracy about 70, 75, maybe 60, and maybe 0 sometime because it returns markdown for you, not your exactly JSON, but you asked to do, okay, return me only JSON. Well, and that's why we need pre-processing. So we get this data from the library and we pre-process. Normalize it, removing some redundant data, remove headers, footers, standardization, trying to make it predictable even on this stage, because everything that you could make deterministic here, you should do that because like LLM. Okay, multi-prompting. You probably have heard about the technique when you use multiple prompts, and in most cases, one prompt is not enough. You have this data, large document, and gigantic prompt for that. And well, the rule of thumb, then when you go about exceed the 30% of context window of LLM, hallucination rate increases. And how to deal with that? Use multiple prompting for each section, for header, for footer, for some like content, you split it with the content, some data, personal data, user data, whatever, depends on your type of document. And you have specific rules. Okay, return me JSON, do not guess what it could be in prompt. Example, what to do, example, not what to do, and that could be gigantic prompt, but only for this section. So yeah, that's increases, but okay, this is costly. You pay 3x token price because you spent much tokens for your, for example, 10 consecutive calls or in parallel calls. Better to have parallel calls. Well, this is example like invoice, extract the document. So we provide the exact data, exact examples for LLM how to parse it. Okay, post-processing, validation. We use Plot Sonnet for parsing, and sometimes it returns Markdown. So even if you ask it to return JSON, it returns Markdown. MD, like MD document, and you could not transfer it to some service, another consumer, because that could break anything. So you validate those data, maybe adjusting like data types. For example, like for the string, you make the number. From the Markdown, you make JSON, even with cropped values, but that's the better. Okay, some missing required fields, maybe some adding some null instead of just undefined absent value in your JSON. Okay, the schema. Okay, you have Pydantic schema, Python schema of our contract, how our JSON should look, and its schema validation, business logic, total minus, like we have for some negative values, some self-consistency, human in loop, even people, they join it to help with that. They evaluate what the result should be. And we used also LLM to evaluate. And this is a bad practice because LLM is really optimistic. Okay, you have everything. Okay, don't worry. Release it. Don't trust me. It's okay, but not not in this case. Yeah, it's dangerous to work to go to the demo with your customer with just LLM evaluation. So end-to-end workflow. So you parse your document, parse your documents, and with some library. That could be OCR library, Textract. They are included in AWS, some parsing system. So you parse your document, you pre-process, you trying to remove some data, unrelated data, trying to simplify the work for the LLM. Then you prompt or multi-prompt. It depends on how documents, large document or simple document, because you should use one prompt for simple documents because token spending, and actually you create a few like system for parsing simple documents, system for parsing complex documents. And because of undeterministic LLM, it could be really complex because we want to avoid the problems from LLM and like makes markdowns or some missing data. Okay, multi-prompts, then extract. LLM, Bedrock, mostly, or it could be Azure.AI or some other systems, because we use it on cloud, mostly, enterprise. Like enterprise, we don't call like OpenAI clients. We use a Bedrock model for that. You extract this data, and then you work with response. You validate it based on your schema, business rules, and you have your evaluation framework. So you should have versioning. So how I change this prompt, how it's reflects on my scores for all documents. always stays at scale. So the main problem here is the scaling for that, because if you use LLM, just, okay, this file is really bad. Could you fix it for me? Fix it. And it's rewrites prompt based for this document. Okay, great. This document improves to 100%. But okay, run another documents that this prompt not adjusted for another documents, and you'll have result decreasing. So you test on scale on all documents, and you get the grade for all of your documents. You should detect regressions, and I think, well, the 94% accuracy, it's really high. 90%, that I think could be production ready parsing system in most cases. And if you want more, it maybe doesn't make sense. I think how we could do more. Well, maybe using specialized models, fine-tuned models for your domain, that could be helpful. So you order the company that have fine-tuned LLM for your specific industry, and it does for you this 95%. They get this maintenance responsibility to have this high score, so you delegate those risks to some company that provides you LLM, fine-tuned LLM based on your data, or you teach your own model with your data. But this is the task of fine-tuning. This another pain. You should have this data prepared, and well, we want everything for today, quickly, without bugs. So fine-tuning, it's like long process. Yeah, version control evaluation. So versioning, yeah. So you change models, you evaluate on the model, how they work. Well, you have the hash from each prompt. Yeah, it's hard. It's hard. It's hard that you cannot rely on it. It could fail on your demo with customer. It's really the problem. But real world result is the best result. I think that's maybe high bar for production. I think 92% would be great. And so build golden set. Firstly, to summarize, build golden set, spend a lot of time for this, spend a lot of efforts, how it should look like, trying to acquire stakeholders to this, and it's really hard, and this is really a boring, painful task. Pre-process everything, reiterate everything, so do not rely on LLM. A lot of scripts. We are lucky that we have now the LLMs that could generate for us those scripts on Python to see most cases, because our post-processing and pre-processing scripts are really huge, but we generate it with LLM mostly. Fusion prompting, like few examples. Validate, yeah, rigorously validate, then test on your all documents on all scale to get this 90-95 accuracy achievable. Yeah, that could be, but it's really hard. But that's the companies really want from LLM. This is really common task, maybe much common than just creating their own model, I guess. So this is like we have RAG chatbot, then we have parsing with LLM. So basically, thank you maybe I was really hurry, or some timing, but I couldn't respond to the questions.
Yes, so now it's time for Q&A. If it's, it's also but first of all, let's thank Andrii for your presentation. Thank you. All right, I can see that there's the first question.
Really well presentation, thank you. Well, description of real problem and great proposal to solve this problem. So you mentioned about multi-use of LLMs, right?
Multi-prompting.
Yeah, about multi-prompting. So on what LLM model did you try? It was like GPT-4 or later on?
Sonnet. We use Sonnet mostly.
Yeah. So the question is, if we would use like GPT 5.2 or like Opus, is it still needed to use multi-prompting, or just those models are pretty well and it's not needed anymore?
Test and scale, and if you use Opus, you pay for tokens. So the framework, like you get the Haiku model, for example, it's the cheapest one, and trying to adjust your framework for that. Use multi-prompting. I think that Opus, it's maybe 10 times higher price than Sonnet regular. Try to use multi-prompts. It's better for you to use multi-prompts than trying to get the expensive model, because it's better to get fine-tuned model, to find some company. There are companies, there are models on Hugging Face, there are millions of models already created. Maybe it makes sense to research, to get from your domain and to use it. Then trying to rely on Opus or some really powerful model, because markdown on your demo with customer, and you will see, you'll get really emotions like so.
All right, thank you.
Thank you.
Great, thank you. I can see more questions. Satya wanted to ask. Okay. Let's pass the mic.
How do you solve those issues? Like data augmentation, or do you do something else?
Number of documents?
Like the cases where the number of documents is an issue, where you don't have the scale to test and validate. Has there been cases like that where you don't have enough documents?
We requested from customer those documents, and we requested different types of documents. This is really related to how you teach your model, AI model, so you prepare data with a lot of edges, a lot of edge cases to make your model reliable. We request from customers different types of documents, real documents with issues, with bugs, to make it happen. Yeah, so that's the responsibility for customer to get out appropriate data.
Thank you for a good presentation. Two small questions from my side. First, have you tried to combine part of validation and extracting by using structured output from LLM, using Pydantic, for example, to ask LLM to generate objects, JSON, with a predefined structure? It is available, as far as I remember, for all models with tool calling functionality. And the second question, have you tried to use historical documents from your customer as a golden set?
Didn't use historical documents. Creating golden set by our team, so didn't have this experience. The first question is when you tool for function calling from LLM to validate.
No. I mean, you can ask your LLM, for example, using Pydantic on the interface side, to provide you a desired structure with according to the schema of your document.
We didn't test it because we want to have our code inside, and we try to not add additional questions to LLM. We want to have much deterministic, and we know that our bedrock we only ask for parse document. Maybe it will be the solution. Maybe you could tell more about how it's effective, but oh no, a lot of problems with bedrock we already have. So, but maybe it could be great choice. Well,
Thank you.
yeah.
Two more questions.
Hey, one more question from my side. You are using PDF as input, don't you?
Sorry?
You are using PDFs as input, don't you? Just PDFs.
PDFs and docs,
Okay,
docx.
unstructured data. Is your layout stable, or it might happen that in the future you will get documents in the layout which is different than what you checked during this validation phase?
It's not stable. We try to standardize it. That's an issue I admire, but that could not be unstable. At least we from LLM, at least we get some expected JSON. So maybe we try to standardize. We use, for example, PyMyPDF for parsing, and we have somewhat structured documents from our customer, and we work with this. And for specific customer, we could have, okay, we have 10 some types of documents, and we work with it. And if you want to do some universal system for every document, well, that's really complicated to make it reliable.
Okay, just heads up. Try with PMU-PDF for LLM. It works better. That's my experience. Okay. And the follow-up question is: are you using then, or what kind of data drift monitoring you're using? Because if you don't have the stable layout, believe me, you will need it.
We have a evaluation framework. Then we test all they have from the libraries and what we have with the bedrock. I agree with you that it's a problem, but we test it just for our custom evaluation framework. Yeah. Okay.
Hi, Andrii. A great presentation. My question is, did you use multi-agentic tools to make the score better, and or did you try use one big LLM with a guideline how it should be and implemented a different kind of the roles so he make better quality of the data?
We tested it. We have one role in prompt, and we do everything by ourselves. Every code, evaluation framework, and but role, as I know, it's not matters much now. We have an update from LLM provider that role it's somewhat not really important, and when you parse data, rely on your pre-processing, rely on your rules in your prompt, rely on the length of your prompt, and rely on post-processing and your evaluation. And maybe drink some alcohol before the demo to be relaxed, because you don't have a guarantee that you'll get predictable results on the customer's demo. Thank you. I wish you to not receive Markdown on your customers demo. Only receive expected JSON.
Okay,
Thank you.
Because I was curious about that because when you have this,
no, I didn't as well. Fortunately not, because we show customer like reliable documents that are really yeah.
okay, because I'm curious that right now we are in multi-agentic when you can specialize every agent from the AI side and give him special role and special guidelines how it should be validated, how to creative after that checking, rechecking, and everything. You can make it workflow and parallel even. And I'm quite curious if you implemented it in a release solution to make the score better, to make less work and more efficient things. Did you try this in approach in any kind of the project?
Currently not. We just we are really in hurry. We don't have capacity for experiments for some agentic systems, and we just use really simple. This system should be really simple to deliver predictable results. Maybe like agents, great, but well, enterprise wants to just parse our document reliably. Okay. Well, but we could discuss it. So of course, I'm really happy to know more about that.
Hiya. So a question from me. So I just wanted to come back to the multi-prompting topic that you talked about. So you've mentioned that you, for example, send a few prompts to the model, but I was wondering, since you, for example, have to send the same input data a few times, I was wondering if this solution is cost efficient. Is it optimal in terms of cost? And what strategies did you do to avoid using sending so much same data again and again to the model?
Pre-processing based on the part of document. So you just pre-process based. So for example, like up to the header, you like sure that you pass all the header there. And sometimes you need some data from other documents also, or from your database. For example, you like have a summary. You fetch from the database and you like enhance your JSON with some summary from another documents, and role. So this is the content. You assign the role. You assign examples. It's not cost efficient, but if the customer wants to be have more reliable system, it could pay 3x for tokens, and well, it depends on the type of customer.
All right, that was the last question. So let's thank Andrii once again. Thank you.
Thank you for a lot of questions. Thank you.
Thanks for answering all the questions and great presentation. And now it's time for our third speaker, Michał.
Okay. Hi, everyone. Thank you for having me here. My name is Michał Grzejdziak-Zdziarski. I'm a machine learning manager at Nomagic, where I've been developing AI systems for pick and place robots for over 6 years. So my talk will be technical, but it will be on rather high level. I will talk similarly to the previous speakers about reliability, but reliability in the context of physical AI. So deployments in physical world, and you can already have a hint that 95% is not enough here, like in this specific domain. I will show you how these requirements arise and what key design decisions we made on our system to satisfy them. So first, simply, what is physical AI? It's just an AI system that interacts with physical world. And this physical world makes everything super messy and super difficult. You can have like humanoid on a street or in a manufacturing facility, right? And it interacts with the whole diversity of a physical world. Similarly, as an autonomous car on in a crowded city, right? Or robotic arm in a warehouse. And what we do actually is robotic arms in warehouses. And I will give examples on based on our experience. One particularly exciting area of physical AI as of today is that of humanoids. Right? There are many startups now that raise tons of money. They make super fascinating research, and they reach super impressive results with capabilities of humanoids. You can have links. You have links here. You can review them later. But humanoids can now do things like folding laundry, right? They can do parkour. They can do lock opening, right? You don't have to open the lock yourself. So now, do you have humanoids at home already? Not really. Not really. Okay. Why? Because it's super difficult, and because every failure here is super costly, right? This is why this is difficult. So these images are AI generated. It wouldn't be bad if they were failed in a way here, but if I had an AI system to interact with real world, this becomes very difficult, right? And typically, what you see here, so if you have autonomous vehicle accident, right, or you have humanoid robot that failed some operation in a manufacturing facility, right, you typically break hardware, and hardware is super costly. In this case, it gets cheaper and cheaper, but it's still costly. And you also have humans, right? So even Gemini or ChatGPT, when generating images, they know that for physical AI failure, you need to call humans, basically. And this is the big cost. So to even consider like production deployment, what you need to satisfy is super high reliability in super high diversity. And this diversity, this is a big thing. So it's easy to record a demo in a lab. Like really, you tell me any capability that you would like to see, that the Nomagic team can build it in a week, right? And show it in the lab. But in production, things get very, very diverse, and many cases, believe me, you cannot imagine before you see it. And in Nomagic, we have the whole charts about things that happened in production and that we didn't realize that can even happen. But it's not only about reliability and diversity, it's also about speed, right? So customers, they care about return on investment, right? So clearly, autonomous vehicle operating at 10 kilometers per hour, you would probably not select it instead of your car, right? You need at least this 50 kilometers per hour. Similarly, for our robots, we have this metric named throughput, like throughput of pick and place operations. So again, picking and placing 600 items per hour, it's much better than 100 items per hour for our customers, right? So you need to prove it also on this part. So again, this is example of a physical AI system. This is what we are doing at Nomagic. We build robots. We build robotic solutions in warehouses, and we need to just empty the bin, right? Empty the bin and pack everything into a pocket sorter. This is one of our typical use cases. So you can see that the robot clearly interacts with physical world, right? And it empties the bin. And what is important here is that actually it's boring, right? Or isn't it? And it has to be boring. And actually, I really liked what one of our customers said when testing our robot. We had a long test, like 2 hours, and it had to stay reliable and consistent. And they said in the end, come on, it was super boring. Right? And this is exactly how it should work. Right? This should be boring. This should be repeatable. This should be reliable. This should be fast. And in our case, this like reliability and speed, this translates to 2 KPIs, very specific KPIs. So autonomy, again, this is average time between 2 human operator interventions. So you saw on the slides before, like every failure requires human intervention. And throughput is just the number of items picked and placed each hour. And let's see what it means actually, right? So let's assume we have throughput 600 items per hour, which is just for mathematical reasons here, because it makes calculation easier. And let's see what happens at different failure rates of our robot, right? So if you're 90%, if you have 90% success rate with this throughput, you get 1 minute autonomy. So every minute you need a human to help the robot. It's completely impractical. No one would even deploy it for a moment, right? If you get to 99% success rate, then you get much better, of course, in terms of autonomy, but it's still 10 minutes, right? So in practice, you need someone around all the time, because every 10 minutes, something can happen, right? So you can understand it as a like pilot level, more or less, right? And then to really bring it to production, you need this 99.9% success rate, right? Because then you get 100-minute autonomy, and this is something that a human operator can handle, having 10 robots, right? 10 robots, 20 robots, right? They can handle them, and then it makes it possible to operate at scale. So let's see what's the technical complexity here, right? So what the robot does is very simple. It just pick item, scan item, push item, right? So as simple as that. But there is one magical variable here that we use, of course, and it's a pick pose that we need to approach. And this is actually like this is the core AI component in our system, right? And we call it grip AI. It takes RGBD picture, right? And this picture goes to grip AI. We have the whole analysis of the image, and we give some pick pose, and it goes to this, let's say, this pick and place, and pick and place this like central controller. It schedules commands to robotic arm. Everything works nicely. Right? So now the interesting thing, we are at Warsaw.AI, right? So I will talk about AI. The interesting thing is what's under the hood of grip AI. Okay, and have you heard about VLMs maybe? Or LLMs? Okay, last talk you had LLMs. So okay, the first thought you could have is, let's just take VLMs and let's ask what they think. And you can select your favorite state-of-the-art VLM. You can give it a warehouse picture. Just select a pick point for a suction cup on any pickable item in the picture, so that the robotic arm can lift this item moving straight up. And I had one model selected. One model selected this red cross, which is not even on an item. Interestingly. Okay, so this is clearly not a way to go, but this was like a very plain way of using LLMs or VLMs. In the last talk, we had many super tricks for this, like multi-prompting, and I will even say that we tried multi-prompting at Nomagic. We did like super optimize this way of like how we prompted the VLMs to really build try to have a picking system based on VLM. This was actually, I will show you on the next slide. I will show you a result for just one of these multi-prompts, and it was 90%, right? So what we can build, and okay, it's in line with the previous presentation, right? You can reach 90, maybe 92, 93% accuracy, and for some use cases it is good, like, but for physical AI system, it's not good. And why it's only 90%? Because these models do not really know our domain, right? They don't know how to pick. They are trained on large scale data, but I think we have orders of magnitude more data about warehouses than ChatGPT was trained on. So what we need actually, like we take these foundation models, right? But we keep this old good data engine approach. Right? You need data. You need, even in the age of LLMs and VLMs, zero-shot learning, agentic systems, like data engine is a key. And I could talk about this very long time, but I have limited time here, right? So I will just go briefly over it and emphasize this one property that we have around our data engine is this incrementality, and this data engine enables us to iterate very quickly with our system. And this happens on 3 levels, more or less, which is data ontology, data selection, and data quality. So we have three actors in all of these components, right? It's production world, it's data engine, and it's grep AI component, right? This grep AI system. What we have in production, like it's huge diversity of the world, right? And you have different items, different containers, different layouts, different actions that you have to take, right? And you have to monitor this diversity, and you need to build on top of this. You need to define still relevant abstractions for the system. Of course, the most typical abstraction, or the first abstraction that you define, is just item, right? We want to pick items, as simple as that. And then you build these capabilities in grep AI. Okay, I can predict items, I can pick items. But then you see more and more categories, so you build on top of them, you build more meaningful abstractions, or you select which abstractions make sense to develop and to use, and then you empower this grep AI component with new capabilities, right? And the important fact that is to make it very fast. Every iteration should be like, in all aspects, you should make these iterations very fast. Now, performance, right? Again, you observe performance in production, right? You observe some SKU that is problematic, and then you need to react quickly, right? Based on this, you need to select good data that maximizes the amount of new information for the current state of the system, right? So we know that in the current state, the system makes mistakes, and we want to meaningfully iterate on the system. We would like to just solve this problem and go to the next problem, not to stack thousands of images for training of this specific SKU, which would be waste of resources, right? So again, you have this loop performance. You select data based on this performance, and you improve the quality of the system. And finally, it's the data quality, but I even changed this here to data annotation operations, which are responsible for this quality. And I think what can be unique in Nomagic, and I think this makes our ML development much easier, is that our labelers are experts themselves, right? They are experts in data, and they are partners to the engineering team to improve the system, right? So it's not only that, you send thousands of data to, I don't know where, like 10,000 kilometers away from us, and you can communicate only in late hours about the quality, and it takes 1 week. No, actually our engineers, they have chats with labelers, and they can respond in 5 minutes to a question about requirements for data. And they can also escalate directly to engineers. They can escalate problems with data, with definition, and communicate corner cases. So if you combine all of this, like if you have this tight iteration loop, what you get is this. So this is just a raw export from our monitoring database, and it's failure rate of grep AI component over time, and it's specifically over last year. So we have some observed values. Of course, they are noisy because there's some randomness in the physical world, but the trend is clear, right? So we, based just on these iterations, we are able to tune the system to perfection, right? So take into account that this is not 5% or 6% or 7%. is 0.05%, right? So it's 5 in 10,000 cases. 5 in 10,000 cases we have a failure caused by our core AI component. So it's amazing. And if we observe a robot just with grip AI, what we see is 99% success rate. How is it so? Right? So the problem is that in many cases you have well, not that many. Like you can solve 99% cases with such a system, but there are situations in real world in which it's not clear what to do. It's not just about picking and placing. You need some complex sequence of actions to make it possible to pick something, right? So here you have one example that the item is stuck in the and cannot get into the pocket sorter system. So we need the robot to actually push it inside. But we can also have source bins in which we just cannot pick immediately. Like we need to push items, we need to topple them, we need to split them in order to be able to pick to pick one piece. So how to solve it? And of course, now the question is, can you just program these actions and build it on top of a perception system? And partly yes, but the truth is that it's super diverse. This is one thing, and this 1%, it's even more difficult than it's much more difficult than this 99%, and it consists of very rare scenarios, like many of them, but all of them are very rare. Like so if you target cases that happen 1 in 10,000 peaks. So to collect a meaningful data sample for this, you need to observe millions of peaks to be able to address this, to even address this issue. Not even saying about measuring whether you solved it in production, right? Because then you need sometimes years to evaluate that you solved it. And another level of complexity here is, of course, that if you can plan 10 actions, like, and you select from 10 possible actions, like if you can plan the sequence of 10 actions and you can select 10 possible actions, then the number of all paths possible here is 10 to the power of 10, and it's intractable for just programming. So what can you do is you take this foundation model again and you train it to control the robot directly, and you do it on a very low level. So you don't embed your preconceptions about picking, toppling, or I don't know, pushing items or moving items, right? You just say, you just train it to move 1 centimeter here, 1 centimeter here, 1 meter here, right? So the system trains to directly understand, to directly control the robot. And it typically can be 15 hertz or 30 hertz or 10 hertz, but basically it can update continuously its actions. But of course you still have this data engine, but this data engine is now maybe simpler. You don't have this whole data ontology that you need to update constantly, but you have just trajectories, like target trajectories for different situations. And we call this component VLA, and this name is like standard research name, which is Vision Language Action, which stems from the fact that these are typically vision language models that produce actions. Right? And this is a solution that we believe scales to this whole diversity, right? And that can solve this all exception cases. And this is how it works. Like you have example here. We have item that is sticking out from the bin, and we cannot send it away in this way, right? And you could program all these situations, but instead you teach the robot to just execute trajectory, and you see that it does. And it's slower than previous videos, but it's slower also because it has to update continuously, like its action. And so in a way, it's by design slower. So in the end, such a system can exist with two such components, right? You have one component that is responsible for perception, and then you can use it for 99% peaks, and it enables like very simple interaction, but also very efficient interaction, because like you have the fastest robot if you just use good old classical robotics, right? Robotics solved the problem of trajectory optimization long time ago, and you can use it just with this perception system, and you can send the command to the robot, and it will execute super fast trajectory. And then you have for this corner cases, you have this direct control system that you use for, let's say, 1% of peaks. It executes slower moves, but it also allows you for advanced interactions, right? For any interaction that you think actually. So if you have the whole system, right, you can see here that to the previous diagram, I added this Nomagic VLA component, right, that can take control over from the pick and place program and can then directly stream to the commands to robotic arm to solve such corner cases. So in the end, we have like this two-level system, one that we use in Happy Path, right? Happy Path, typical case, you execute super fast, you are very stable, but if anything strange happens, you fall back to this complex case system, which is direct control. So if you combine these two, right, this is how you get to 99.9%. And in Nomagic, we are scaling. We have this kind of system for both Happy Path and for complex cases. And we have tens of robots and not only like pilot deployments, thanks to this approach. So in the end conclusion, right, production grade physical AI requires exceptionally high reliability and high speed, right? And to strike the best balance, you can combine two systems, this for Happy Path and for complex case system, for complex case handling. And you still need to keep this data engine to enable quick development iterations to to handle the diversity of the real world. And that's it. Thank you for listening.
Amazing results. Thanks, Michał. Okay, do we have questions to Michał? Great.
Hello, thank you for the presentation. It was really great to hear about your solutions and problems. So I have a question about the RGBD topic that you mentioned, that you use such images for as your input. And I have a question, two connected questions actually. Do you use stereo cameras to obtain the depth, and whether you tested currently used solutions for depth estimation, for example, meta depth anything or something?
That's a good question, and the answer is yes and yes. So the thing is that like depth estimation, like even classical depth estimation, this is a super hard thing, as it turns. And you have some cameras that are, that are quite okay. You can start with them, but they are cheap. You can order tens of them, but their quality is lacking, right? And you can have problems to reach this kind of reliability just due to bad input. At the same time, there are cameras like industry grade cameras that are super high quality, right? And their error is like 1 millimeter, 2 millimeters maybe. Now the key is where we see the possibility for depth estimation, and we tested depth anything. We use it for some aspects in our development, but it's not of this quality as top industry grade cameras. But what's interesting in depth estimation for us is to have corrupted camera, like that is very cheap, but you can improve it to this industry grade camera based on RGB input as well. Okay. So in this case, we are working on this too.
Hi, thank you for the talk. I would like to ask about the VLA system. If you are training the VLA system, what kind of training are you using? Is it reinforcement learning or is it like a completely different paradigm? And the same with Grip.AI as well. How do you train that system? Like what kind of system are you using to train it?
Yeah, so typically VLA is trained for via imitation learning, right? So it's kind of you train it to imitate human generated trajectories, or not only human generated trajectories, but basically you provide in kind of a supervised way, right? You provide just target trajectories. And Grip.AI, so Nomagic exists for 7 or 8 years actually, right? So we started building our system back then, and it's mostly supervised system with some aspects of self-supervised training and unsupervised training, with some experiments around reinforcement learning, right? But to really keep stability, right, and quality of the system consistent, this is mostly supervised learning.
Okay, thanks.
Hi, I have a little bit different question because when we see you need very high, let's say, using the CPU, GPU, and others component and the cloud and data processing. So how is estimated? Because you saw that it's multiple different kind of the image. After that is analyzing data, transformation and processing. So how it when you make the estimation compared to the human? Because I'm quite curious, how was the ratio when you make it in the production scale?
And you mean specifically in what aspect compared to human, like speed or?
Speed, money, and time.
Okay, so speed, money, and time. Let's maybe start with money. So in terms of money, we sell robots to customers that really see return on investment with this, right? So the pricing is such that we can build a meaningful business model on top of this, right? And at the same time, customers, we have business model, we have margins on top of this, and customers also have benefits from this, right? So this is like value for customers is clear here, and there are also other components for our customers, like rotation of work or of workforce is huge in their use cases, right? Because people don't really like to work 8 hours a day doing pick and place actions, right? It's mundane, and they cannot focus all the time. And this is this gets me to like the question of quality, and depending on use case, on customer, on specific warehouse, humans do mistakes like 1% of time, more or less. Maybe it's 0.5, maybe it's 1.5, and in the end, what you see is order that is that is shipped incorrectly to the end consumer, right? So we can have you ordered 2 iPhones and you get 1, or you ordered in worst case you order 2 bottles of medicine and you get 1, or you get some other medicine. And in this case, like depending on use case, we are our robots are of better quality than humans. Right?
Okay, and I'm curious, you use the cloud solution on-prem on the client when you install all those kinds of things.
Yeah, so our system is on-prem, right? It's because it simplifies and it's for customers, and it reduces latency. Again, this is the matter of speed. So like speed, throughput, we collect tons of data like to monitor our system, and transmitting it over cloud in real time. This would add big delays on latency.
Okay, thank you.
Okay, last chance to ask a question now.
Thank you for a very interesting presentation. In your opinion, what okay, as I understood, so now we could have some simple robots, big or something, some simple. What could be the breakthrough when you will see like reliable plumber robot, reliable like electricity technician, and something? What could be the breakthrough? Or could be the chain of robots only? Do you see like this breakthrough, or it's we far from that?
So this is a big discussion in robotics industry right now. And there's a discussion between generalist and specialist approaches, right? So there is a promise, and many companies are betting for it, that we are very close to generalist models. And if you see these companies that develop humanoids, they claim it and they raise tons of money to deliver it. It's very difficult, right? It's very difficult. It's similarly, I would say, to an extent, it's similarly difficult to getting VLMs to these levels of 99.9%. But who knows, right? Maybe they are right. On the other side, you have this specialist approach that is, you address a specific task, and to address it, you target a market. And if on this market you can make money and building the solution, then you can do it. But I'm not sure if like electricians or plumbers is this market, right? Because costs of creating such a specialized solution is so high that probably no one would do it at the revenue that they can generate on this market. So we'll see. Maybe we'll have generalized models in 5 years. I think that all of us learned from last 10 years that it's very hard to predict the next 10 years.
All right, very true. Thanks. Thank you, Michał. Let's thank Michał once again. Happy to chat.